Video 53 of the Master Course Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is now optical rotation. We've seen before in the beginning of this chapter that the linear or plane polarized radiation can be expressed mathematically as the superposition of left and circularly polarized waves which have the same refractive index. Now, if the refractive index between left and right circular polarized light differ in this way, so the difference between left minus right is not zero, then the superposition will still lead to a plane polarized wave. As you can see here, that is just the expression for a plane polarized light in a medium having this refractive index. But this plane polarized wave is now the plane of the polarization of this plane polarized wave is rotated compared to the original wave, meaning the wave where the difference between left and right refractive index is zero. And the angle by which this wave is rotated, you can see from here, that is the angle, that's the same here. That's the angle by which the plane of polarization is now rotated. And that is called the optical rotation. A medium for which the refractive index of left and right circularly polarized waves are different, which means that left and right circularly polarized waves propagate with different velocities. Such a medium is called circularly birefringent. Birefringent in general means that the refractive index for the motion, two different types of motion through the material are different. And here, if it's the refractive index of the left and right circularly polarized waves is different, one says circularly birefringent. And chiral molecules have precisely this property because the two enantiomers will interact differently with the left or right circularly polarized waves, which means the interaction of one of the enantiomer with the right one will be different than the left one, which then leads to a difference in the refractive indices. Now, if you want to derive the molecular property which describes this effect, then we cannot use the dipole approximation any longer, because in the dipole approximation we assume that the electric field is uniform over the extent of the molecule. So here the perturbation is not only going to be the uniform electric field, that of course would lead again to the polarizability, but the non-uniform electric field, or more precisely the variation of the field over the extent of the molecule, meaning the derivative of the field, the spatial derivative of the field, or the field gradient, and we will express it here in terms of the curl of the time-dependent electric field. So we'll look at the expansion of the induced dipole moment in the presence of the homogeneous part of the electric field and this curled of the electric field. Now, one could do that, but actually one does it slightly different, because one uses Maxwell's third equation, which relates the curl of the electric field vector to the time derivative of the magnetic field vector. So we're going to look at the expansion of our dipole moment now in the presence of left and right circularly polarized light, which means we have the permanent dipole moment and induced dipole moment, and there will be sort of two different ones, one because of left and one because of the right circularly polarized light. And we expand this now in, of course, the homogeneous left and right circularly polarized light, and then in the derivative of the corresponding magnetic field vector of the left and circularly polarized light, the derivative with respect to time. And we get again two proportionality constants, both of course tensors. Here we have the well-known electric dipole polarizability, and here we get a new one, and we write this as 1 over the frequency omega 1 times this property here, which is called the mixed, and we'll see that later why, the mixed frequency dependent electric dipole magnetic dipole polarizability enhancer. And we can of course define again an isotropic value as being the sum of the diagonal elements divided by 3. With this expansion now here, we can then look at the refractive index of a microscopic sample of nonpolar molecules, where in addition to the polarizability term, which we already had in the section before, we get an additional contribution from this mixed electric magnetic dipole polarizability here. And there's a difference in the sign depending on whether we look at the refractive index of the left or right circularly polarized light. And then if we take the difference between the refractive index for left, which is with the minus sign, and the one with for right, which is with the plus sign, then the difference between the two is actually just this mixed electric magnetic polarizability times the number density divided by the speed of light and the vacuum dielectricity constant. And that means that the angle of rotation is actually given as the product of this G prime tensor here, the frequency dependent electric dipole magnetic dipole polarizability times the frequency of the radiation. Which means if you want to calculate this angle of rotation of the plane of polarization, then we have to calculate the frequency dependent electric dipole magnetic dipole polarizability. And we're going to derive an expression for this now in the same way as for the polarizability. We just have to look at what is our perturbation here. So we're going to look again at the expectation value of our dipole moment operator in the presence of perturbation. So it's a time-dependent expectation value of the dipole moment operator, but now the perturbation is the presence of the time-dependent magnetic induction of the left and circular polarized radiation. And here's the expression which we had seen before in the first section of this chapter. Now, magnetic induction, be it time dependent or not, enters the Hamiltonian in a linear quadratic term. And if we now consider only closed shell molecules, so there is no interaction with the spin of the electrons, just with the angular momentum of the electrons, and we only look at the linear term, so we consider it to first order, then our first order perturbation Hamiltonian is the magnetic induction times this perturbation operator, and the perturbation operator is just the magnetic dipole moment operator, the angular momentum magnetic dipole moment operator. And combined with the expression for the magnetic field for the left and circular polarized light, we get this expression. So we can identify our perturbation operators. We have two, because we have left and right, so we have two, where one of them is either minus or plus the magnetic dipole moment operator in one direction, and the other is just a magnetic dipole moment in the perpendicular direction. And then the field here, because in all this case here, we now look only at monochromatic radiation in the contrast to what we did for the dipole polarizability, frequency-dependent dipole polarizability in the last chapter, where we looked at a polychromatic radiation. So here we look only at monochromatic radiation, which means from the integral over the frequencies, or the Fourier transformation of the frequencies, we have to pick out the frequency we're interested in, which is omega 1, by these two Dirac delta functions. Now, inserting these perturbation operators in these expressions for the fields in our normal time-dependent response theory expansion of a time-dependent expectation value, we get that the time-dependent expectation value in the present either of left or right circularly polarized light. So in principle, it's two equations, but I combined them here in one. And the upper signs are always for the left and the lower signs are for the right one. So it's the permanent electric dipole moment. And then we get some response functions. And in total, we get now here 4 response functions because we have two different perturbation operators, one in the I and the other one in J direction. And then we have two different fields with two different frequencies. So we get these 4 response functions. Well, the difference between this one and this response function is that this is for plus omega 1 and this is for minus omega 1. And here again, for the where we have the magnetic dipole moment operator in the J direction, we also have one for the positive frequency and one for the negative frequency. Now making use of the symmetry properties of response function, and here we have a response function with a real and a purely imaginary operator. Um, uh, the symmetry relation with respect to a change of the sign of the frequency, we can combine this together in one response function and accordingly changing the signs of the exponentials, which gives us this expression here. So that's where we have combined two of the response functions together. Now, that is just cosine, and this is then, because of the minus sign, is sine. So we end up with this expression here, where we have the response function in the I direction combined with cosine, and the response function in the J direction combined with a sine. Before we continue, we should remember what is the expression for the time derivative of the magnetic induction of left and right circular polarized light. And that looks precisely like this, where we also have cosine and sine, which basically means that we can rewrite the expression from the page before with, instead of with two terms, with cosine and sine, we can identify that this is actually just the time derivative of the magnetic induction for left and right. So we end up here with a time derivative multiplied with just one response function. And please note that this is a scalar product here. And if we compare this with our expression for the refractive index in the presence of left or right circular polarized light, then we can see that our frequency-dependent mixed electric dipole magnetic dipole polarizability tensor G prime is actually also again just one response function. Is this response function where we have as the first operator the electric dipole moment operator and as the second operator the magnetic dipole moment operator. And because the electric dipole moment is a real operator, the magnetic dipole moment is purely imaginary. So this response function is going to be purely imaginary. But because we have an I in front of it, the G prime tensor is going to be real. Now, as we've done it for the polarizability, we can of course calculate this response function by using all these matrix representations which we had derived in chapter 3, but we also can use the sum over states, the spectral representation of the response function, as I've done here, with the two terms, one with a positive frequency and one with a negative frequency again. And like for the polarizability, we can now try to, or we can bring it on a common denominator. But the result is slightly different than in the case of the frequency-dependent polarizability. We still get that also this G prime tensor in the denominator here has the frequency squared, and the difference between the frequency of the radiation squared and the energy difference between the excited state and the ground state. But up here in the numerator, we now have the frequency of the radiation. And this, of course, means that if the frequency of the radiation is 0, this mixed frequency-dependent magnetic electric dipole polarizability G prime tensor is actually zero, which makes, of course, a lot of sense because the phenomenon we are trying to describe is that an electromagnetic waves, or circular polarized electromagnetic waves, move through a material. Um, and if the frequency of that wave is zero, there is no wave. And of course, then we don't have the effect.